Good day everyone. In this video, I'm going to discuss the accumulation points in topological spaces. Actually, the concept is similar or analogous to the accumulation points in the topology of the line and plane. Now, let's have the definition of the accumulation points in topological spaces. So we let X be a topological space. A point P here in X is an accumulation point or limit point. Also, it is called cluster point or derived point of a subset A of X if and only if for every open set G containing P contains a point of A different from P. That is, we have this one, for any open set G containing P, we will show this one, this condition. So as you observed here, the condition is the same in the accumulation points in the topology of the line and plane. So still, the set of accumulation points of A, we have this notation, is called the derived set of A. Now, let's try to consider, by the way, G here is an open neighborhood containing point P. Or simply, we call G as an open set. When we say open neighborhood, we mean any open set containing this point P. So, this notation here is called the deleted open neighborhood of P. So that is an open set G without P. Okay, so let's have this example here. Let X be the set with these elements. And then let's try to consider this topological space, tau, here. And say A is the set, say ABC. Okay, say this is our set ABC. So set A. Now in this case, we are going to find the limit point of A. Take note, to find the limit point of A, CX, limit point of A rather, CP, which is our limit point, must belong to X. Not only in A, but in X. So we will test all the possibilities. It means we will test all the points in X if that point is a limit point of A by satisfying the condition using the definition of an accumulation point. So let's start. For P, let's start for P equals this one, A. So we will get any open sets containing A. So for open sets containing A, we will try to look into our topology. So recall that the members in the topology are all open sets. So of course, the open sets containing A, we have this set. Of course, set X contains A. This set contains A. Another one, we have this set. And that's it. So we only have 3 sets containing A. And those 3 sets are our G in our definition. So G, open set containing point A, point P. So this is G, G, another G here. So we will show this condition. We have G minus A. We have P here is A. So the open deleted neighborhood of A intersection set A. What is our set A? Set A is the set A, B, C. Okay. And it should not be empty. So it should not be empty in this case. So here, let's have, so it's not empty. Take note, if this condition is not satisfied, you can directly conclude that that point is not a limit point of the set. So first, for G, let's have here X. So we have X minus A intersection. We have our A is A, B, C, D. So what is X minus set A? So we delete A from the set X. So what is left? We have B, C, D, E. So we have B, C, D, and E. And then we're going to get it the intersection from A, B, C, D. So what's the intersection? Of course, the intersection is B, C. Therefore, this is not empty. So the condition is satisfied. Now let's have another G. Of course, we have set A. So we have set A minus A, set A, and then we intersect it to set ABC. So of course, set A minus set A is empty. And then intersection set ABC. Of course, what's the answer? Of course, this is empty. Now take note, for G equals set A, if we are to show this condition, it is empty. So this condition is not satisfied. So if it is in that case, if there is only one open set G here, wherein this condition is not satisfied, we can conclude that A is not a limit point of A. Set A. A is not a limit point of A. Is it clear? So in this case, A is not a limit point of A is not a limit point of A. So let's try to test when P is equal to B. And we will do the same process to test whether point B is an accumulation point of set A. So we will show this condition. So we have here an open deleted neighborhood of B intersection to the set A. Now, so what are these sets G here? So this set G is an open set containing point B. So let's try to look at our topology. Open set containing B is of course X. Containing B is, we have this one. Therefore, we do have to test two sets only here. So first, we have set X. So we have X minus B intersection set ABC is equal to, of course, this is minus B. We have A, C, D, E. Intersection to A. So it is empty or not? It is not empty because the intersection of this is A, B, C. So we have AC. So AC, intersection A. The intersection is the set AC. Another one, if we have here, we have set BCD. So we have set BCDE minus B intersection ABC. So we have minus this one. So what is left? We have CDE. So we have CDE and then intersection ABC. So the intersection is C. Therefore, it is not empty. Hence, we're done showing any open sets here in our topology containing B. And we have shown that this condition is satisfied for all open set G containing B. So we can say that B is a limit point of A. That is. So we have shown already that B is a limit point of A. Now for point C here, the open sets containing C are X, this set, and this set. Notice that if we take this as our G, we have CD minus C intersection to ABC. This is equal to set D intersection ABC, and the intersection is empty. So this condition is not satisfied. So C is not a limit point of A. Now take note that any one lang ang di mo satisfy, so we can say nga dili siya limit point. So kaniwa man siya ni satisfy. So that's it. Now to test for point D, we need to show this one. Now the open sets G containing D, point D are X. We have CD, we have ACD, and BCD. So we will do the same process, and we can show that D is a limit point of A. If we will do the same process as before. Now to test for, by the way, this is a limit point, so let's put check there. And then for P equals E, we will show this condition here, this one. So open sets containing E, we have two sets only. We have set X and this set. So you show this set, and then we can show that for G equals X, this will be satisfied, and then for G equals this one, this also will be satisfied. Therefore, we can say that point E is a limit point of the set A. So we have here, in this example, we have three limit points of A. Therefore, we can say that the derived set of A is equal to this set with elements B, D, and E. So that's it. It's as simple as that. So in my next lecture, I will discuss another example. In which we're going to get the accumulation point of the given set.